Yeah, we are dealing with the notation, this summation notation. We want to prove that this square deviations is equal to this simplified from here. So how can we do that? So let's go and prove it. The first thing, we're going to expand this this expression inside the sigma. So expanding the expression, we are having this x bar squared. So when we expand, we're gonna have this expression now. We know that when we have got sigma and terms under sigma, we can actually split the terms if they are adding. So if you have got a sigma a plus b, so if all these if these two are under a plus are under this sigma, we can actually split them. If they add or subtract, we can actually get this expression. So we're gonna go on and do the same with this. We're gonna actually split this. So splitting it, this gonna give us now. We know also that the we know that when we have got a sigma, and then when you have got a sigma, the summations, and then we have got a constant a, this constant can actually be pulled here in front. So this can be equal to a. So with the constant pulled outside of the sigma notation. So we can actually do the same. So here we're gonna have the same aix squared. So this one here, because remember the bar and 2, they don't have subscript I, which means they are not the sums, they are not the summations. So they are considered as constant, so they can be pulled outside. So it's gonna have 2x bar xi. Then here we know that if you have got a summation and there is a constant c, and there is we have got summation of the terms xi with the constant c, which is this c is actually multiplying all the terms xi, which means I is 1, 2 up to n. So actually we can pull out c. Okay, c can be pulled out. I hope that you know this from calculus 1 when we were dealing with estimating an integral. Now we also know that if we have got a summation of the constants, okay, of a constant, for example, a constant a, how do you know that's a constant? It's a constant if it does not have a subscript I, okay, or any other subscript which shows that it's a series, like the additions. We can actually we can actually multiply by n, which means this actually is equal to na. So we just have to take the number of the terms in a series multiplied by the constant. So having that in mind, we know that this one, it does not have a subscript I. So x bar squared does not have subscript I, so it can be written as n times x bar squared. Again, we know that x bar is equal to the summation of all x, okay, divided by n, which is the x bar actually is a sample mean, okay, is a sample mean or average, is actually average. If you are taking statistics, you understand that x bar is an average. So actually the sum, so if you have got an average which is equal to the summation of all the terms divided by their number, so if you want to get the summation, you take average, which is n times x bar, which is equal to the summation of all the terms. So in that means that wherever we have got this notation, we're going to replace it with nx bar. So we are having this expression, so 2x bar. So here this is gonna be replaced by nx bar multiplied by nx bar, and my here there is positive, I forgot to put that, so it's positive nx bar squared. Okay, so we can simplify this. X bar times x bar, that is 2x bar squared. So, and there is n, okay, then plus nx bar squared. So we have the coefficient -2, so this can be simplified to this final expression. Yeah. So this is the expression that we are looking for. So this is very useful, especially in statistics. We know that the sample, actually what is known as sample deviations, or we know that sample variance is given as all the square deviations, then you divide by n minus 1, which is the sample size minus 1. So this can be simplified to 1 over n minus 1 multiplied by the summation of the summation of all x I squared, then minus n x bar squared. Yeah, you're gonna find this formula in more often in statistics. And then deviation, sample deviation, standard deviation, then you just have to take the square root, which means you take the square root of this, you get the sample deviation.